We thought we knew how many galaxies exist in the observable universe. For decades, astronomers worked with a comfortable number. They estimated around 100 billion galaxies filled the cosmos, scattered across the vast darkness of space. Each galaxy contained hundreds of billions of stars. The numbers were already staggering, almost beyond human comprehension. 100 billion galaxies meant more stars in the universe than grains of sand on all of Earth's beaches combined. The cosmos seemed impossibly large, filled with light and matter and possibility, stretching to the limits of what we could observe. Then, in 2016, everything changed. A team of astronomers analysed data from the Hubble Space Telescope, using new techniques that could detect fainter, more distant galaxies than previous methods allowed. They combined observations from multiple deep field surveys, images where Hubble stared at tiny patches of seemingly empty sky for days at a time, collecting every photon of light from the most distant objects. What they found shocked the astronomical community. The universe did not contain 100 billion galaxies. It contained closer to 2 trillion galaxies. 2,000 billion galaxies filling the observable cosmos, 20 times more than we had previously believed. This was not a small correction or minor adjustment to our understanding. This was a fundamental revision of how much stuff exists in the universe. Overnight, the cosmos became far more crowded than anyone had imagined. Those 2 trillion galaxies represented an almost incomprehensible amount of matter and energy. Each galaxy contained billions or trillions of stars depending on its size and type. The total number of stars in the observable universe jumped from roughly 1 septillion to 20 septillion. That is 20,000 trillion stars. More stars than seconds have passed since the Big Bang, more stars than thoughts any human has ever had. The numbers became so large they lost practical meaning. We can write them mathematically, but cannot truly grasp them intuitively. The discovery raised immediate questions. Where were all these galaxies? Why had we not seen them before? The answer lay in distance and time. Many of the newly counted galaxies existed in the very early universe, billions of light years away. Their light had been travelling toward us for most of cosmic history. By the time that light reached our telescopes, it had been stretched by the expansion of space into infrared wavelengths that earlier surveys missed. These ancient distant galaxies were small and faint, containing fewer stars than the massive spiral and elliptical galaxies we see in our cosmic neighbourhood. But they existed in enormous numbers, filling the early universe with light. Other missing galaxies were closer, but hidden behind dust or located in regions of the sky that surveys had not yet covered completely. Some dwarf galaxies orbiting near larger galaxies got washed out by the glare of their bright neighbours. Each refinement in observational technique revealed more galaxies that had been lurking undetected. The universe kept surprising us with how much it contained. Every time astronomers thought they had completed the census, new technology or better analysis methods revealed that we had undercounted. The 2 trillion number itself might not be final. Some estimates now push even higher as we include the faintest, smallest, most distant galaxies. But something about this discovery troubled researchers. It was not just that we had missed so many galaxies. That could be explained by observational limitations and the difficulty of detecting faint objects. What troubled astronomers was what happened when they started looking at how these galaxies moved and how they were distributed across space. The patterns did not match predictions. Galaxies appeared grouped in ways that seemed strange. Vast regions of space contained far fewer galaxies than expected, while other regions appeared unusually crowded. The cosmic web, the large-scale structure formed by galaxies clustering along filaments of dark matter, showed anomalies that made no sense. Astronomers began noticing that when they measured the motions of galaxies, something seemed wrong with the numbers. Galaxies were moving differently than gravity alone could explain. Not just slightly different, dramatically different. Entire clusters of hundreds of galaxies appeared to be flowing in the same direction, as if pulled by some enormous, unseen mass. But there was nothing there. Empty space stretched in the direction of motion. No large cluster of galaxies. No obvious gravitational source that could cause such large-scale flows. Just darkness and the subtle glow of the cosmic microwave background radiation. They called it the dark flow. Clusters of galaxies spanning hundreds of millions of light years, all moving together at speeds of several hundred kilometers per second toward a region of space beyond our cosmic horizon. This violated everything cosmologists thought they understood about the universe. After inflation, after the Big Bang smoothed everything out, matter should be distributed uniformly on large scales. Galaxies should be moving away from each other due to cosmic expansion, with only small local variations caused by the gravitational pull of nearby structures. Large-scale coherent flows like the dark flow should not exist. There was nothing in the standard model of cosmology that could cause them. Other anomalies emerged. The Hubble constant, which measures how fast the universe is expanding, gave different values depending on how you measured it. Observations of the cosmic microwave background predicted one expansion rate. Direct measurements of galaxies and supernovae gave a different rate. The discrepancy was small, only about 10%, but it persisted across multiple independent measurements using different methods. 10% might not sound like much, but in precision cosmology, it represents a crisis. The difference was too large to be explained by measurement error. Something was fundamentally wrong with our understanding of cosmic expansion. Then astronomers discovered that the universe's expansion was not just happening, it was accelerating. Distant supernovae appeared fainter than they should, indicating they were farther away than expected for their redshift. Space itself was expanding faster and faster over time, driven by some mysterious force that physicists called dark energy. This dark energy made up roughly 70% of all energy in the universe. Yet nobody had any idea what it was. The best theory predicted its value should be 10 to the power of 120 times larger than observations allowed. This was the worst prediction in the history of physics, off by more than 100 orders of magnitude. The distribution of galaxies themselves showed peculiarities. Computer simulations of how the universe should look, based on our best understanding of gravity and the Big Bang, produced structures that looked similar to what we observed, but not quite right. The simulations predicted more small satellite galaxies orbiting large galaxies than we actually found. They predicted satellite galaxies should be scattered randomly around their hosts, but observations showed satellites often aligned in planes or disks. The largest structures in the universe, enormous walls of galaxies stretching billions of light years across space, seemed too large to have formed in the time since the Big Bang. Every measurement, every new survey, every refinement in our observations revealed that something was off. The universe contained far more galaxies than we thought. Those galaxies moved in unexpected ways. They were distributed in patterns that seemed wrong. The expansion of space was accelerating for unknown reasons. Dark matter held galaxies together but remained undetected despite decades of searching. Dark energy pushed the cosmos apart but defied explanation. We had mapped billions of galaxies across cosmic history. We had traced the large-scale structure of the universe. We had measured the expansion rate and the age and the composition of everything we could see. Yet the more we learned, the more we realized how little we actually understood. The crisis in cosmology was not that we lacked data. We had more data than ever before. Telescopes on the ground and in space mapped the positions and motions of hundreds of millions of galaxies. Surveys catalogued objects across the entire electromagnetic spectrum, from radio waves to gamma rays. Computational power allowed simulations of cosmic evolution at unprecedented resolution. The crisis was that the data did not fit together. Different measurements gave conflicting answers. Observations contradicted predictions. The standard model of cosmology worked brilliantly to explain the cosmic microwave background and the large-scale uniformity of the universe. But when astronomers looked closely at galaxies and their distributions, nothing quite made sense. Something was missing from our picture of reality. Either we misunderstood gravity on cosmic scales, or dark matter and dark energy were more complex than simple mathematical terms and equations, or the universe contained structures and influences we had not yet detected. Some researchers began wondering whether the anomalies pointed to something even stranger. Perhaps our universe was not as isolated as we assumed. Perhaps other realities were influencing how galaxies moved and how space expanded. Perhaps the 2 trillion galaxies we had found were only part of a larger cosmic story. Perhaps what we were seeing was evidence that our universe was touching something beyond itself, something hidden, something that made its presence known through the strange behavior of galaxies across billions of light years of space. Galaxies should not all be moving in the same direction. After the Big Bang, after inflation smoothed out the early universe, matter should be distributed uniformly on the largest scales. Yes, gravity causes local clustering. Stars collect into galaxies. Galaxies collect into groups and clusters. Clusters connect along filaments of dark matter forming the cosmic web. But these structures span hundreds of millions of light years at most. Beyond that scale, the universe should look uniform, average, the same in all directions. Galaxies should be moving away from each other due to cosmic expansion, with only small peculiar velocities caused by the gravitational pull of nearby structures. This is what the standard model predicts. This is what decades of theory and observation suggested was true. Then in 2008, Alexander Kashlinsky and his team published results that shattered this assumption. They had been studying the motion of galaxy clusters using data from the Wilkinson microwave anisotropy probe satellites. The technique was clever. Hot gas in galaxy clusters scatters photons from the cosmic microwave background radiation. This scattering, called the kinetic Sunyaev-Zeldovich effect, distorts the temperature of the background radiation in a way that depends on the cluster's velocity. By measuring these distortions for hundreds of clusters, the team could map how clusters moved relative to the cosmic microwave background. What they found should have been impossible. Clusters spanning an enormous region of space, more than 600 million light-years across, all appeared to be flowing in the same direction, not slowly drifting, moving rapidly at speeds around 1,000 kilometers per second. All of them, hundreds of galaxy clusters, containing thousands of individual galaxies, all moving together like a vast river of matter flowing through space. The direction of motion pointed toward a region of the southern sky between the constellations of Centaurus and Vela. But there was nothing there, no supercluster large enough to gravitationally pull so many galaxies, no obvious structure that could explain the motion. Kashlinsky called this the dark flow. The name captured both its mysterious nature and the fact that whatever caused it remained invisible. The discovery sparked immediate controversy. Some astronomers questioned the methods, suggesting the signal might be noise or systematic error in the data. Others tried to replicate the findings using different techniques and different data sets. Several independent studies confirmed that something unusual was happening with the motion of galaxy clusters. The dark flow was real, perhaps not exactly as originally reported, perhaps with different speeds or affecting a different region of space than first claimed, but something was pulling or pushing enormous numbers of galaxies in ways that standard cosmology could not explain. The problem was fundamental. In the standard cosmological model, based on Einstein's general relativity and the Big Bang theory, large-scale structure forms from tiny quantum fluctuations during inflation. These fluctuations get stretched to cosmic size and become the seeds for galaxy formation. Gravity amplifies the denser regions, while less dense regions expand into voids. This process creates the cosmic web we observe, but it operates locally. Structure on one side of the observable universe forms independently from structure on the other side. There is no mechanism to create coherent flows of matter across scales larger than a few 100 million light-years. Yet the dark flows spanned much larger regions. Where could such motion come from? One possibility was that something beyond our cosmic horizon was gravitationally pulling the galaxies. The observable universe has a finite size because light has only had finite time to reach us since the Big Bang. Currently, we can see objects up to about 46 billion light-years away, accounting for cosmic expansion. But the universe likely extends far beyond this horizon. Matter outside the observable universe has gravity. Could massive structures beyond our horizon be pulling visible galaxies toward them? The mathematics said no. Gravity falls off with distance. Structures would need to be absurdly massive and absurdly close, just beyond the horizon, to create the observed flows. And inflation should have smoothed out such enormous structures. Their existence contradicted what we knew about the early universe. Another possibility was that our models of cosmic evolution were incomplete. Perhaps dark matter and dark energy behaved differently on the largest scales than we assumed. Perhaps gravity itself worked differently when averaged over billions of light-years. Modified gravity theories had been proposed to explain galactic rotation curves without dark matter. Could similar modifications explain the dark flow? Researchers explored many variations. None provided a satisfying explanation without breaking something else. The theories either contradicted other well-established observations or required fine-tuning of parameters to absurd precision. Then some cosmologists suggested something that sounded like science fiction. What if the dark flow was evidence of other universes? In eternal inflation theory, our observable universe is one bubble among countless others. Most bubbles remain forever separated by exponentially expanding space. But before inflation completed, while our bubble was still small, it might have been close enough to other bubbles to feel their gravitational influence. Those other universes would pull matter in our universe toward them. The pull would create large-scale flows exactly like what observations showed. As our universe expanded and inflation separated the bubbles, the gravitational connection would weaken, but the motion would persist. Galaxies would continue flowing in the direction they were pulled billions of years ago, when other universes were close enough to affect us gravitationally. This explanation was controversial for obvious reasons. It invoked other universes that we cannot observe directly. It relied on inflation theory, which, while widely accepted, remained unproven. It required that bubble collisions or near collisions occurred at just the right time and distance to create the observed flows, without creating other effects that we have not detected. Many cosmologists dismissed the idea as too speculative. The dark flow needed explanation, yes, but reaching for parallel universes seemed premature when conventional physics might still account for the observations. Yet the conventional explanations kept failing. More data accumulated. The Planck satellite provided even better maps of the cosmic microwave background. Studies using different methods and different wavelengths of light measured galaxy motions. Some studies found evidence supporting the dark flow. Others found no evidence or suggested the effect was smaller than originally claimed. The scientific literature became a battlefield of conflicting results and competing interpretations. What everyone agreed on was that something strange was happening with how matter moved on the largest cosmic scales. Additional anomalies emerged. The cosmic dipole, a pattern in the cosmic microwave background caused by our solar system's motion through space, gave a velocity that seemed too high. Our local group of galaxies moves at about 600 kilometers per second relative to the cosmic microwave background rest frame. This motion should be caused by the gravitational pull of matter within a few 100 million light-years. But when astronomers catalogued all the nearby matter and calculated its gravitational effect, the numbers did not quite work. Something was pulling us faster than the visible matter could account for. More dark matter than expected, different dark matter distribution, or influence from beyond the observable universe. Large-scale structure showed other oddities. The cosmic web was not as uniform as simulations predicted. Some regions appeared more clustered than probability allowed. Enormous walls and voids exceeded the size that should have been possible, given the age of the universe and the speed at which structures grow through gravitational collapse. The Sloan Great Wall, a vast chain of galaxies stretching over 1 billion light-years, challenged theoretical limits. The Hercules Corona Borealis Great Wall appeared even larger, perhaps 10 billion light-years across. Structures this large should not exist. They required more time to form than the universe had been in existence. Yet there they were, defying our models. Every anomaly could potentially be explained individually. Measurement error here, statistical fluctuation there, theoretical assumption needing adjustment elsewhere. But the anomalies kept accumulating. The dark flow was not an isolated puzzle. It was part of a broader pattern, suggesting our cosmological models were missing something fundamental about how the universe evolved and how matter distributed itself across the largest scales. Either the standard model needed significant revision, or something beyond the standard model was influencing cosmic structure. Something we had not detected. Something that made its presence known through the unexpected motions and distributions of billions of galaxies scattered across billions of light-years of space. Something that remained frustratingly hidden despite our best efforts to find it. The universe is expanding. We have known this since Edwin Hubble's observations in the 1920s showed that distant galaxies were moving away from us. The farther away a galaxy was, the faster it receded. This was not because galaxies were moving through space away from some central point. Space itself was expanding, carrying galaxies along with it. This discovery revolutionized cosmology and led to the Big Bang theory. If the universe is expanding now, it must have been smaller and denser in the past. Wind back time far enough, and you reach a moment when everything was compressed into an infinitely hot, infinitely dense state. The Big Bang, the beginning of space and time as we know it. For decades, astronomers worked to measure exactly how fast the universe was expanding. This expansion rate is called the Hubble constant, named after Edwin Hubble. Knowing this number is crucial for understanding cosmic history. It tells us the age of the universe. It tells us how far away distant objects are. It connects to the universe's composition, how much matter and dark energy and dark matter exist. The Hubble constant is one of the most important numbers in all of cosmology. Measuring it accurately became a top priority for astronomers worldwide. Two main methods emerged for measuring the Hubble constant. The first used the cosmic microwave background radiation. This ancient light from when the universe was 380,000 years old carries detailed information about cosmic conditions in the early universe. The temperature fluctuations across the sky depend on physical processes that are well understood. By measuring these fluctuations precisely and comparing them to theoretical models, cosmologists can infer the expansion rate. The Planck satellite provided exquisite measurements of the cosmic microwave background. Analysis of this data gave a Hubble constant of about 67 kilometers per second per megaparsec. This means that for every megaparsec of distance, about 3 million light-years, the recession velocity increases by 67 kilometers per second. The second method used direct observations of galaxies and supernovae. Certain types of stars and stellar explosions have known intrinsic brightnesses. By measuring how bright they appear from Earth, astronomers can calculate how far away they are. Compare this distance to the galaxy's redshift, how much its light has been stretched by cosmic expansion, and you can determine the expansion rate. Adam Rees and his team used Hubble Space Telescope observations of Cepheid variable stars and Type Ia supernovae to make extremely precise measurements. Their result gave a Hubble constant of about 73 kilometers per second per megaparsec. At first, this discrepancy did not seem too concerning. The difference was less than 10%. Measurement uncertainties could potentially account for it. But as observations improved and uncertainty shrank, the discrepancy persisted. More data made the problem worse, not better. The two methods gave answers that were incompatible within their measurement errors. One of them had to be wrong, or both were right, and something fundamental was missing from our understanding of cosmic expansion. Cosmologists call this the Hubble tension. The name understates the severity of the problem. This is not a minor disagreement that better measurements will resolve. This is a crisis that threatens the foundations of modern cosmology. If the early universe measurements are correct, then the universe is expanding slower than direct measurements indicate. Where did the extra expansion come from? If the direct measurements are correct, then the early universe had different properties than we think. The cosmic microwave background would need to be reinterpreted. Fundamental parameters like the density of matter and the strength of dark energy would change. Either way, the standard model of cosmology is incomplete or incorrect. Dozens of research teams have checked and rechecked both measurements using different methods and different datasets. The Hubble tension remains. The early universe method consistently gives values around 67. The direct measurement method consistently gives values around 73. Multiple independent teams using different instruments and different analysis techniques get the same discrepant results. This is not systematic error from one telescope or one research group. This is a robust, reproducible disagreement that has persisted for over a decade, despite intensive effort to resolve it. What could explain the Hubble tension? One possibility is that dark energy is more complex than we thought. The standard cosmological model treats dark energy as a constant, the cosmological constant that Einstein introduced and later called his greatest blunder. This constant represents energy inherent in empty space itself. It does not change with time or location. It simply exists, pushing space to expand faster and faster. But what if dark energy evolves? What if it was different in the early universe than it is today? This could reconcile the measurements. The cosmic microwave background would reflect early universe expansion, affected by weaker or differently behaved dark energy. Modern expansion would be faster due to stronger dark energy today. This sounds promising until you try to build a physical model that works. Every attempt to make evolving dark energy explain the Hubble tension requires fine-tuning parameters to unlikely values or produces side effects that contradict other observations. Another possibility is that our model of the early universe is incomplete. Perhaps something happened between the time the cosmic microwave background was emitted and today that we do not account for. Extra radiation in the early universe could change how we interpret the cosmic microwave background. New particle physics beyond the standard model might affect cosmic evolution. Some researchers propose that neutrinos, ghostly particles that barely interact with matter, might have unexpected properties that alter cosmic expansion. Others suggest undiscovered particles or fields could be involved. Each proposal requires new physics that has not been confirmed by any experiment. A more radical possibility is that we are misunderstanding something fundamental about how we measure distances or redshifts. Perhaps Type Ia supernovae, the standard candles used for direct measurements, are not as uniform as we assume. Perhaps their brightness varies systematically with cosmic time or environment in ways we have not detected. Extensive studies of supernovae have found no evidence for such variations, but researchers continue searching. Or perhaps our local region of the universe is unusual. If we live in a large, underdense void, local expansion rates could differ from the cosmic average. Measurements of local structure find no evidence for a large void, but some researchers argue We have not looked carefully enough. Then there are explanations that sound like science fiction. What if the Hubble tension is evidence that our universe is interacting with other universes? In some multiverse theories, universes can be close enough in higher dimensional space to exert gravitational influence on each other. This influence would affect expansion rates. The early universe might have been influenced differently than the modern universe if the configuration of nearby universes changed over time. Or perhaps the collision between bubble universes that might have caused the cold spot also affected cosmic expansion in ways we have not properly accounted for. These ideas remain highly speculative. Most cosmologists do not take them seriously because they invoke unobservable entities to explain the unexplained. Yet the conventional explanations keep failing. The Hubble tension has become one of the most important unsolved problems in cosmology. It is not just an isolated puzzle, it connects to other mysteries: the nature of dark energy, the distribution of matter across the universe, the physics of the early cosmos. The tension suggests our standard model is incomplete at a fundamental level. Something we think we understand, we actually do not. Either our measurements are more wrong than we believe, which seems increasingly unlikely given how many independent checks have confirmed both sides, or our theoretical framework is missing crucial physics. Perhaps dark energy behaves in ways we have not imagined. Perhaps gravity works differently on cosmic scales than general relativity predicts. Perhaps the universe is not as simple and uniform as we have assumed. Or perhaps, just perhaps, the influence of other realities is making itself known through the incompatible expansion rates we measure. If our universe touched or continues to touch other universes in ways we have not yet understood, those interactions could affect how space expands. The effects might be subtle, just enough to create a 10% discrepancy in measurements. Just enough to confuse us. Just enough to make us question everything we thought we knew about cosmic expansion. The Hubble tension might be the universe trying to tell us something important, something about its nature, something about what lies beyond the boundaries of what we can directly observe, something hidden that nevertheless makes its presence felt through the strange behavior of cosmic expansion across billions of light years and billions of years of cosmic history. Computer simulations of galaxy formation produce beautiful results. Input the initial conditions from the Big Bang. Add dark matter, normal matter, gravity, gas physics, star formation rules. Let the simulation run forward billions of years of cosmic time. Watch as structure emerges from the primordial soup. Dark matter collapses into halos. Gas falls into these halos. Stars ignite. Galaxies form and grow. The simulations reproduce many features of the real universe remarkably well. The cosmic web appears. Galaxies cluster along filaments. Voids open up in between. On large scales, simulated universes look convincingly like our own. But zoom in, look at individual galaxies. Compare simulations to observations in detail. Problems appear. The most glaring is the missing satellites problem. Simulations predict that large galaxies, like our Milky Way, should have hundreds or thousands of small satellite galaxies orbiting them. These satellites form when small clumps of dark matter collapse early in cosmic history. Most remain dark, containing too little normal matter to form many stars, but dozens should be bright enough to detect. Each should contain anywhere from thousands to millions of stars. They should surround the Milky Way in all directions, scattered randomly across the sky. Astronomers count the actual satellite galaxies orbiting the Milky Way. They find about 50, not hundreds, not thousands. 50, even accounting for satellites too faint to detect or hidden behind the Milky Way's disk. 50, the numbers do not match. The discrepancy is not small. Simulations predict at least 10 times more satellites than we observe, possibly 100 times more, depending on how you count. Where are the missing satellites? Did they never form? Were they destroyed? Are they still out there, but invisible for some reason we do not understand. The problem is not unique to the Milky Way. Andromeda, the nearest large galaxy to us, shows the same deficit. It has even fewer satellites than we do, perhaps 30 bright enough to detect. Other large galaxies examined carefully show similar patterns. Everywhere astronomers look, they find far fewer satellite galaxies than dark matter simulations predict. This has been known since the late 1990s. Decades of work have failed to resolve it satisfactorily. Every proposed solution creates new problems or requires assumptions that seem contrived. One explanation is that the missing satellites exist but contain too few stars to see. Perhaps most small dark matter halos never formed stars efficiently. Gas in these tiny halos might have been heated by the first generation of stars in the universe, preventing it from cooling and condensing into new stars. Or perhaps supernovae explosions in the small halos blew most of their gas out into intergalactic space before many stars could form. These satellites would still exist as dark matter clumps, but would be essentially invisible. This sounds plausible until you examine it carefully. Studies of how gas behaves and how star formation works in small halos suggest this cannot completely explain the discrepancy. Some satellites should still be bright enough to detect more than we see. Another explanation is that dark matter is more complex than we assume. Standard cold dark matter simulations treat dark matter as particles that interact only through gravity. They move slowly in the early universe, allowing structure to form on small scales. But what if dark matter interacts with itself or with normal matter through forces we have not detected? These interactions could suppress the formation of small dark matter halos while leaving large halos unaffected. Self-interacting dark matter or warm dark matter could solve the missing satellites problem. The issue is that no experimental evidence supports these alternative dark matter models. Every attempt to detect dark matter particles or interactions has failed. We know dark matter exists because we see its gravitational effects, but we know nothing else about it with certainty. A more troubling possibility is that our simulations are fundamentally wrong about how structure forms. The standard cosmological model is built on general relativity and the assumption that dark matter and dark energy behave in specific simple ways. If either assumption is incorrect, simulations based on them would produce wrong predictions. Modified gravity theories that attempt to explain galactic rotation without dark matter also predict different numbers of satellites. Some of these theories better match the observations, but they fail to explain other phenomena that standard dark matter explains beautifully. No alternative theory works as well overall as the standard model, despite its satellite problem. Then there is the planes of satellites problem. This makes the mystery even stranger. The satellites we do observe around the Milky Way are not randomly distributed as simulations predict. About half of them orbit in a thin plane, like planets orbiting the Sun. This plane is called the vast polar structure because it is oriented nearly perpendicular to the Milky Way's disk. The satellites in this plane move coherently, orbiting in the same direction. Simulations say this should be incredibly rare. Satellites should be scattered in all directions. Finding them organized into a coherent plane is like flipping a coin 100 times and getting all heads. Technically possible, but so unlikely that it suggests something is wrong with our assumptions. Andromeda has the same problem. Its satellites also preferentially orbit in a plane. So do satellites around several other nearby galaxies that have been examined carefully. The pattern repeats. This cannot be coincidence. Something about how satellite galaxies form or survive creates these planar structures. But what? Simulations do not produce them. The standard model cannot explain them. Researchers have proposed that satellites might form from tidal debris, material stripped from smaller galaxies that merged with the main galaxy. This debris can orbit in planes, But this explanation requires an implausibly large number of past mergers and makes predictions about satellite properties that do not match observations. Some researchers suggest the problem indicates that our understanding of galaxy formation is incomplete in ways that have nothing to do with dark matter or cosmology. Perhaps satellites form preferentially in certain directions due to the way gas falls into galaxies from the cosmic web. Filaments of dark matter connect galaxies. Gas flows along these filaments. Satellite galaxies might form preferentially along the filaments, creating the appearance of planes. This sounds promising until you check whether real filaments are oriented in the right directions to explain observed satellite planes. They are not. The orientations appear random. Others propose more radical solutions. What if satellites are not independent galaxies at all, but were ejected from the main galaxy during violent events in the past? What if some force we do not understand destroys most satellites shortly after they form? What if the distribution of dark matter around galaxies is fundamentally different from what simulations predict due to physics we have not yet discovered? Each proposal struggles to explain all aspects of the observations without creating contradictions with other well-established facts. The missing satellites problem and the planes of satellites problem together suggest that something is seriously wrong with either our simulations or our theories, or both. We are not slightly off in our predictions. We are off by factors of 10 to 100. Our predictions about satellite distributions are not slightly wrong. They are completely wrong. This is not the kind of discrepancy that minor adjustments fix. This is a fundamental failure that points to missing or incorrect physics in our models, and it connects to the other anomalies. The motions of galaxies across the universe do not match predictions. The expansion rate of the universe depends on how you measure it. Now, the number and distribution of satellite galaxies make no sense. Each problem could potentially be explained individually with enough creative thinking and adjustment of assumptions. But the problems keep multiplying. The universe keeps surprising us with behavior that does not match our carefully constructed models. We have mapped billions of galaxies. We have simulated cosmic evolution in exquisite detail. Yet basic predictions about how many small galaxies should exist and where they should be found fail dramatically when tested against observations. Something is off, something fundamental, something we have not yet understood despite decades of effort and observation and theory. The galaxies are trying to tell us something. We just have not figured out what it is. The universe had a beginning. The Big Bang occurred 13.8 billion years ago. In the time since, space has been expanding and structures have been growing through gravitational collapse. This process has limits. Gravity works at the speed of light. It can only pull matter together from finite distances in finite time. This means there is a maximum size for structures that could have formed in the age of the universe. Calculate this limit using our understanding of gravity and cosmic expansion, and you get a number. No structures should span more than about 1.2 billion light years. Anything larger would require more time to assemble than the universe has existed. This is not controversial. This is basic physics applied to cosmology. Then astronomers found structures larger than this limit, not slightly larger, much larger. In 1989, Margaret Geller and John Huchra discovered the Great Wall. This was not a wall in any physical sense, but rather a vast sheet of galaxies stretching across hundreds of millions of light years. At the time, it was the largest known structure in the universe, spanning about 500 million light years at its longest dimension. This was surprising but not completely shocking. It pushed against theoretical limits, but did not obviously break them. Perhaps the formation models needed refinement. Perhaps such large structures could form given the right initial conditions and enough time. Then astronomers found larger structures. In 2003, the Sloan Great Wall was discovered. This vast chain of galaxies and galaxy clusters stretched over 1.3 billion light-years. It exceeded the theoretical size limit. Computer simulations could not easily produce structures this large in the available time. The discovery challenged cosmological models. Perhaps dark energy behaved differently than we thought. Perhaps initial conditions in the early universe were lumpier than standard inflation predicted. Perhaps our calculations of maximum structure size were too conservative. Theorists worked to explain how such large structures could form without abandoning the standard cosmological model entirely. Before that debate settled, astronomers found an even larger structure. The Hercules Corona Borealis Great Wall was identified in 2013 by analysing the distribution of gamma-ray bursts. These extremely luminous explosions mark the deaths of massive stars. Their positions trace the distribution of galaxies across the universe. When astronomers mapped where gamma-ray bursts were occurring, they found an enormous concentration spanning 10 billion light-years. 10 billion. The theoretical maximum was 1.2 billion. This structure was nearly 10 times too large to exist. It should not be there. The time required for gravity to assemble something this vast far exceeded the age of the universe. Yet there it was, undeniably present in the data. The problem is not just size, it is probability. Even if we imagine that somehow structures could grow faster than models predict, the statistics are still wrong. In a universe that started out smooth and uniform, random quantum fluctuations during inflation created small density variations. These variations grew through gravitational collapse into the structures we see. The statistics of these fluctuations are well understood. They predict how common structures of different sizes should be. Finding one structure slightly larger than expected might be a statistical fluke. Finding multiple structures significantly larger than expected suggests the statistics are wrong. Something about the initial conditions or the growth process does not match the standard model. The Sloan Digital Sky Survey and other large galaxy surveys have mapped hundreds of millions of galaxies across billions of light-years. Analysis of these surveys reveals that the universe is lumpier on large scales than it should be. There are more large structures, more significant density contrasts between filled and empty regions, more organization extending across enormous distances. The cosmic web itself, while broadly matching simulations, shows differences in detail that accumulate into a significant discrepancy. The universe has more structure on large scales than our best models predict, given the amount of time available for that structure to form. Some astronomers argue the problem is not as severe as it appears. Defining structure size is tricky. The Hercules Corona Borealis Great Wall is not a solid object, but rather a region where galaxies are slightly more concentrated than average over an enormous volume. Perhaps calling it a single structure is misleading. Perhaps it is better understood as a statistical fluctuation in galaxy density rather than a bound or forming structure. By this reasoning, the theoretical size limits apply to virialized structures, regions that have collapsed and settled into equilibrium. Large-scale density fluctuations might extend over larger scales without violating physical limits on structure formation. This argument is technically correct, but misses the point. Even if these enormous structures are not virialized, they still represent density contrasts that should not exist at their scale. The statistical distribution of matter should be more uniform on scales of billions of light-years. Finding significant inhomogeneities at these scales indicates that something happened to create more structure than random inflation fluctuations should produce. Either the initial conditions were different from what standard inflation predicts, or structure grew faster than standard gravity and dark matter allow, or we are observing some pattern that has nothing to do with gravitational structure formation. That last possibility sounds absurd but deserves consideration. What if some of these large-scale structures are not produced by gravitational collapse? What if they represent something else? Correlations in galaxy positions could potentially arise from influences acting during the early universe. If bubble universes collided at multiple points, those collisions could create patterns in how matter distributed itself. These patterns would look like structure, but would not have formed through the normal process of gravitational growth. They would be imprints from events that occurred before normal structure formation began. This might explain why they violate size limits. They are not structures that grew, they are patterns that were imposed. Another speculative idea is that the universe underwent multiple phase transitions early in its history. During these transitions, energy density variations could have been imprinted on space at enormous scales. These variations would affect where galaxies formed billions of years later, creating the appearance of structure spanning scales larger than gravity could produce. This sounds exotic, but is not entirely outside mainstream physics. The electroweak phase transition and quantum chromodynamic phase transition definitely occurred in the early universe. Perhaps other transitions happened that we do not yet understand. Perhaps those transitions left marks on large-scale structure, or perhaps the problem indicates that our understanding of cosmic expansion is wrong in ways that affect structure formation. If the expansion rate evolved differently than standard models predict, structures would have more or less time to grow. The Hubble tension shows we do not fully understand expansion. If expansion was slower in the past than current models assume, structures would have had more time to grow and could reach larger sizes. This does not immediately solve the problem, because slower early expansion creates conflicts with other observations. But it suggests that fixing the expansion history might address multiple anomalies simultaneously. What troubles cosmologists most is not that one or two large structures exist. It is that every time we survey a larger volume of the universe, we keep finding more and larger structures pushing against or exceeding theoretical limits. The pattern suggests our models systematically underpredict how much structure exists on the largest scales. This is exactly opposite to what we would expect if the models were basically correct, but we had been unlucky and observed atypical regions. If the models were right and we were seeing flukes, sometimes we should find regions with less structure than predicted. Instead, we consistently find more. The discrepancy is systematic, not random. The existence of impossibly large structures is another piece of evidence that something is wrong with our cosmological models. Combined with the dark flow, the Hubble tension, the missing satellites and other anomalies, a picture emerges of a universe that does not behave as our theories predict. Each problem could individually be explained away with sufficient creativity and adjustment of assumptions. But the accumulation of problems suggests something more fundamental. Either our theories about structure formation are significantly incomplete, or our observations are being systematically misinterpreted, or the universe contains influences we have not accounted for. Influences that might originate beyond the boundaries of what we can directly observe. Influences from other realities perhaps, leaving their marks on the distribution of billions of galaxies across impossible scales of space. Galaxies should point in random directions. Their rotation axes should be oriented every which way across the sky. When you look at a large sample of galaxies, the number spinning clockwise should equal the number spinning counterclockwise. The orientations should show no preference for any particular direction. This is a basic expectation from the cosmological principle. The universe is isotropic, meaning it looks the same in all directions. If galaxy orientations showed systematic patterns or preferences, that would violate isotropy and contradict the foundation of modern cosmology. In 2014, astronomers analysing data from the Sloan Digital Sky Survey found something disturbing. The rotation axes of spiral galaxies were not randomly oriented. Across an enormous region of space spanning hundreds of millions of light-years, galaxies showed a tendency to align with each other. Their spin axes pointed preferentially in similar directions. The alignment was not perfect, not every galaxy participated, but statistically, the pattern was significant. Far more galaxies aligned than random chance would allow. This should not be possible. There is no known mechanism that could cause galaxies separated by such vast distances to coordinate their spins. More studies followed using different galaxy surveys and different methods. Some confirmed the alignment signal, others found no evidence for it. The scientific literature became a confusing mess of contradictory results. Part of the problem was statistical. Defining galaxy orientation from two-dimensional images is tricky. Measuring alignment between galaxies requires careful analysis, accounting for observational biases and selection effects. Different research teams used different methods and came to different conclusions, but several large independent studies found statistically significant alignment extending across scales that should show no correlations. The scale was crucial. Galaxies close together can influence each other gravitationally. Their orientations can become correlated through tidal forces or past interactions. This is well understood and creates alignment on scales up to a few million light-years. But the observed alignments extended over hundreds of millions of light-years. At these scales, galaxies are causally disconnected during most of their history. Light has barely had time to travel between them since the Big Bang. They have never interacted, yet somehow their spins showed correlations. Another strange pattern emerged. The alignment was not uniform across the sky. It appeared stronger in certain directions. Galaxies seemed to preferentially align with the cosmic web, the filamentary structure formed by dark matter. This made some sense. Galaxies form within dark matter halos that are part of larger filamentary structures. Gas falls into galaxies along these filaments. The infall could create torques that spin galaxies in particular directions related to the filament orientation. Computer simulations showed this could produce alignment on moderate scales, but the observed alignments extended beyond what simulations predicted. Some researchers found evidence that galaxy alignments pointed toward specific regions of the sky. One study suggested spiral galaxies in one hemisphere of the sky preferentially pointed toward the northern galactic pole, while galaxies in the opposite hemisphere pointed away from it. This created a dipole pattern in galaxy orientations. Such a dipole should absolutely not exist in an isotropic universe. If real, it would indicate some large-scale asymmetry in how the universe evolved. Perhaps something pulled or pushed matter preferentially in one direction during galaxy formation. This connected to other anomalies. The dark flow showed matter moving preferentially in one direction. The cosmic microwave background showed a dipole in temperature that was larger than expected from our motion through space. Now galaxy orientations showed possible dipole patterns. Different observations all hinted at large-scale anisotropy in the universe. All suggested the cosmological principle might be wrong. The universe might not be isotropic, after all. Something broke the symmetry. Something created preferred directions in cosmic evolution. Explaining galaxy alignments requires either new physics or cosmic events we have not considered. One possibility is that magnetic fields in the early universe were stronger and more organized than currently believed. These fields could torque gas clouds as they collapsed to form galaxies. If magnetic fields had coherent structure on large scales, they could create correlated galaxy spins. The problem is we have no evidence for such strong early magnetic fields. Current theory suggests cosmic magnetic fields were weak and tangled during galaxy formation. Trying to make them strong enough to create the observed alignments requires speculative physics. Another possibility is that dark matter distributions had unexpected correlations on large scales. If dark matter halos preferentially formed with aligned angular momentum across enormous regions. Galaxies forming in those halos would inherit that alignment. But why would dark matter have such correlations? The initial conditions from inflation should produce halos with random angular momenta. Creating correlated angular momentum requires something to impose order during or after inflation. Perhaps turbulence in the dark matter distribution, perhaps phase transitions that created preferred directions, perhaps something else we have not imagined. Or perhaps the alignments tell us about cosmic inflation itself. Some inflation models predict that quantum fluctuations during inflation might produce correlations on enormous scales. These correlations could affect not just density, but also angular momentum. Galaxies forming from correlated initial conditions would show aligned spins. This is theoretically possible, but requires specific inflation models that differ from the simplest versions. Testing this would require extremely precise measurements of galaxy orientations across large volumes of space. Then there are more exotic explanations. What if the alignments reflect the geometry of space itself? If the universe has curvature or topology that differs from what we assume, space might naturally create preferred directions. Galaxies would align with these geometric features. This sounds bizarre, but is not entirely outside physics. We know space can be curved by mass and energy. Perhaps the overall shape of space has features that affect galaxy formation in subtle ways we have not accounted for. Or what if the alignments are evidence of interactions with other universes? If our universe touched other bubble universes during early cosmic history, those interactions could have created asymmetries. Energy transfer during bubble collisions might flow preferentially in certain directions. This energy would affect how structure formed, potentially creating correlations in galaxy properties, including spin orientations. The collisions would impose patterns on our universe that look like mysterious, large-scale alignments. This explanation requires the multiverse to be real and requires that collisions left specific types of marks that we can observe in galaxy surveys. The debate continues. Some astronomers argue the alignment signals are not statistically robust enough to trust. Observational systematics and analysis choices can create spurious patterns that look significant but are actually artifacts. Without independent confirmation from multiple surveys analysed multiple ways, we should not conclude that large-scale alignments exist. Others argue the signals are real and reproducible. The patterns appear in different datasets using different methods. Dismissing them as artifacts ignores compelling evidence that something unusual is happening with galaxy orientations. What everyone agrees on is that if the alignments are real, they are deeply puzzling. They should not exist in the standard cosmological model. They require either modification of that model or addition of new physics or both. Combined with the other anomalies, the dark flow, the Hubble tension, the impossible structures, the alignment patterns contribute to a growing sense that our understanding of cosmic evolution is incomplete. The universe behaves in ways we did not predict and struggle to explain. Billions of galaxies scattered across billions of light years apparently coordinate their properties in patterns that should not be possible. Something is off, something we have not yet figured out despite decades of observations and increasingly sophisticated theoretical models. The galaxies know something we do not. They're aligned for reasons we cannot explain, and those reasons might connect to the hidden influences affecting cosmic structure on the largest scales. Most of space is empty. Galaxies cluster along filaments of dark matter forming the cosmic web. Between these filaments stretch vast voids containing very few galaxies. This pattern emerges naturally from gravitational collapse. Denser regions attract more matter and become denser still. Less dense regions lose matter to their surroundings and become emptier. Over billions of years, this process amplifies initial tiny density variations into the dramatic structures we observe. Computer simulations reproduce this beautifully. Input the initial conditions. From the Big Bang. Let gravity do its work. The cosmic web emerges with filaments, clusters, and voids all appearing in the right proportions, except some voids are emptier than they should be. These supervoids contain far fewer galaxies than even normal voids. They span hundreds of millions of light years across. The largest known supervoids are genuinely enormous structures where the galaxy density drops to a tiny fraction of the cosmic average. Finding a few such voids is not necessarily surprising. Statistical fluctuations should occasionally produce regions slightly emptier than average, but the observed supervoids are not slightly emptier. They are dramatically emptier, and they appear more common than probability allows. The Boötes supervoid was discovered in 1981. This enormous region spans 330 million light-years across. Within this volume, astronomers found only 60 galaxies. A typical region of space this size contains tens of thousands of galaxies. The Boötes void contained less than 1% of the expected number. Such an extreme underdensity should be incredibly rare. Yet there it was, impossible to miss once someone thought to look for it. Astronomers nicknamed it the Great Nothing because it was so conspicuously empty. Other supervoids have been found since. The Giant Void. In the constellation Canes, Venatici spans 1.3 billion light-years. Multiple other voids exceeding several hundred million light-years in diameter have been catalogued. Each is far emptier than simulations predict should exist. The probability of finding even one supervoid, this empty and this large, is tiny. Finding several suggests either we have been extraordinarily unlucky in our observations, or the universe produces voids differently than simulations predict. The voids are not completely empty. Galaxies do exist within them, just far fewer than normal. These void galaxies are interesting in their own right. They are typically smaller, bluer, and younger than galaxies in denser regions. They are still forming stars, while galaxies in clusters have mostly shut down star formation. This makes sense. Void galaxies have fewer neighbours and therefore experience fewer interactions that could disrupt star formation. They evolve in peaceful isolation, while their cousins in dense regions are shaped by mergers and environmental effects. But why are the voids so empty in the first place? Initial density variations from inflation created regions slightly above and below average density. Overdense regions collapsed and became more overdense. Underdense regions expanded faster than average and became more underdense. This process is well understood. Simulations show exactly how voids form and grow. The problem is that starting from the initial conditions we observe in the cosmic microwave background, simulations do not produce voids as empty as we observe. To get supervoids as extreme as the Boötes void, initial conditions would need underdensities significantly larger than inflation predicts. Where did those extreme underdensities come from? One possibility is that the initial conditions were not as smooth as standard inflation predicts. Perhaps quantum fluctuations during inflation had a different statistical distribution than the simplest models assume. Perhaps inflation lasted longer in some regions than others, creating more extreme variations in density. This requires modifications to inflation theory that are possible but lack independent support. We need inflation to explain the large-scale uniformity of the universe, but now we also need it to explain large-scale non-uniformities like supervoids. Balancing these requirements is tricky. Another possibility is that voids grew larger and emptier than simulations predict because dark matter or dark energy behaved differently than we assume. If dark matter interacted with itself, its distribution might evolve differently. If dark energy was stronger in underdense regions, it could push matter out more efficiently and create emptier voids. Modified gravity theories that change how gravity works on large scales might also affect void formation. Each of these alternatives faces challenges. We have no evidence for self-interacting dark matter or spatially varying dark energy. Modified gravity theories must explain many phenomena beyond void formation, and most fail at some point. Supervoids also create observable effects beyond just being empty. Light passing through underdense regions loses less energy to gravity than light passing through average density regions. This makes the cosmic microwave background appear slightly cooler when seen through a void. This is the integrated Sachs-Wolf effect. Astronomers can search for this signature by correlating cold spots in the cosmic microwave background with the positions of voids identified in galaxy surveys. Several such correlations have been found. The voids do create temperature decrements, as expected, but some voids create larger temperature effects than theory predicts. The cold spot we discussed earlier was initially explained as being caused by a supervoid, but analysis showed that even a supervoid as large as the Eridanus void could not produce a temperature effect as large as observed. The temperature deficit was 2 or 3 times larger than the integrated Sachs-Wolf effect could explain. This contributed to the idea that the cold spot might have a different origin, perhaps a bubble universe collision. If standard voids cannot explain the cold spot, perhaps it is not a standard void. Other voids might have similar issues. When astronomers measure their temperature signatures carefully and compare to theoretical predictions, the observed effects sometimes exceed what integrated Sachs-Wolf alone can produce. This suggests either our calculations are missing something, or voids affect the cosmic microwave background through additional mechanisms we have not accounted for. Perhaps they affect dark energy differently than we think. Perhaps they create gravitational effects beyond what general relativity predicts. Perhaps something else is happening that we have not imagined. The existence of supervoids also connects to the Hubble tension. Measurements of the local expansion rate depend on distances to galaxies. Those distances are calibrated using various standard candles and rulers. If we happen to live near a large void, the local expansion rate could differ from the cosmic average. Matter flows out of voids faster than the average expansion rate. Galaxies in and near voids recede faster than galaxies at the same distance in average density regions. This could bias our measurements of the Hubble constant upward, making the local universe appear to expand faster than the early universe indicates. Studies have searched for evidence that we live in a large void. Most find no evidence for a significant local underdensity at the scales required to explain the Hubble tension. We would need to be near the center of a void spanning billions of light years, much larger than any known supervoid. Observations of galaxies out to several 100 million light years show no evidence for such a large void. The galaxy distribution around us looks fairly typical, but some researchers argue we have not looked carefully enough or at large enough scales. The debate continues. The supervoids remain puzzling. They are too empty, they are too large, they are too common. Simulations struggle to produce them. Theory struggles to explain them. Every solution proposed creates new problems or requires unlikely assumptions. The voids seem to be telling us something about cosmic structure formation that we do not understand. Perhaps inflation created more extreme variations than standard models predict. Perhaps gravity works differently on large scales. Perhaps dark energy or dark matter has properties we have not yet discovered. Or perhaps the voids are clues to influences from beyond our universe. Perhaps interactions with other realities during the early cosmos created both the supervoids and the superstructures, the extreme emptiness and the impossible filaments, the anomalous hotspots and cold spots scattered across billions of light years. Perhaps what we are seeing is not just structure formation, but the aftermath of cosmic contact. Evidence that our universe is not isolated after all. The cosmic microwave background is the most uniform thing we have ever observed. Temperature variations across the sky amount to only about 1 part in 100,000. This incredible uniformity is exactly what inflation predicts. The early universe was stretched smooth by exponential expansion. Any large-scale irregularities got diluted away. What remained were tiny quantum fluctuations, also stretched to cosmic size, that became the seeds for all structure. The cosmic microwave background captures the moment when these seeds first became visible in ordinary matter. The temperature map is exquisitely uniform, with tiny variations that match theoretical predictions almost perfectly. Almost. Several anomalies persist in the cosmic microwave background that do not fit the standard model. We have discussed the cold spot, the largest and most dramatic anomaly, but other strange features appear in the data that trouble cosmologists. None are as extreme as the cold spot. None individually would cause much concern, but together they create a pattern of deviations from the expected statistical properties of the temperature map. The deviations are subtle but real. Multiple independent analyses by different teams using different methods confirm them. The cosmic microwave background is not quite as perfect as it should be. One anomaly is the lack of correlations on the largest angular scales. Temperature fluctuations at different points on the sky should be correlated in specific ways depending on their angular separation. These correlations encode information about cosmic geometry and the processes that created the fluctuations. Cosmologists quantify correlations using mathematical functions called angular power spectra. The shape of the power spectrum tells you about physics in the early universe. Inflation makes precise predictions about what the power spectrum should look like. Measurements of the actual cosmic microwave background show that the power spectrum matches predictions very well on most angular scales, but on the very largest scales, corresponding to angles greater than about 60 degrees across the sky, the measured power is lower than expected. There is less correlation at large angles than there should be. The deficit is not huge, only about 10 to 20%, but it persists across multiple missions and multiple analysis methods. The probability of this occurring by chance is small, around 1 to 2%. Not impossible, but unlikely enough to be interesting. Why would large-scale correlations be suppressed? One possibility is that the universe is finite and smaller than we thought. If space has a size comparable to the observable universe, certain wavelength fluctuations cannot fit. Like standing waves on a string, only specific modes are allowed. This would suppress power at large scales. The cosmic microwave background would show less correlation on the largest angles because those correlations would require fluctuations larger than the universe itself. This sounds bizarre, but is actually well defined mathematically. Some cosmologists have explored finite universe models that match the observed power spectrum better than infinite universe models. Another possibility is that inflation did not last as long as standard models assume. If inflation ended slightly earlier, quantum fluctuations on the largest scales would not have been stretched as much. They would enter the observable universe with different properties than smaller scale fluctuations, potentially suppressing power at large angles. This requires fine-tuning the duration of inflation to match the observations, which makes theorists uncomfortable. Why would inflation end at exactly the right moment to create the observed anomaly? Pure chance seems unlikely. Some physical process must have controlled when inflation ended. But what? Another persistent anomaly is called the axis of evil. This dramatic name refers to the fact that several features in the cosmic microwave background appear aligned with each other and with the geometry of the solar system. The quadrupole and octupole, mathematical descriptions of temperature patterns at specific angular scales, are not oriented randomly as they should be. They point preferentially toward particular directions in space. Those directions correlate suspiciously well with the ecliptic plane, the plane in which planets orbit the Sun. This should absolutely not happen. The cosmic microwave background originates from the edge of the observable universe, nearly 14 billion light-years away. It has nothing to do with our solar system, which formed billions of years later in an ordinary part of an ordinary galaxy. Finding correlations between the cosmic microwave background and local solar system geometry makes no physical sense. It is like finding a message in the oldest light in the universe that references modern Earth geography. The only reasonable explanation is that this is a coincidence or an artifact of how we analyze the data. Extensive studies have searched for instrumental, systematics, or analysis choices that could create the axis of evil. None have been found that fully explain it. The alignment appears in data from multiple satellites processed by independent teams. It survives different methods of removing foreground contamination from our galaxy. It persists when different parts of the sky are analyzed separately. The axis of evil seems to be real. But if it is real, it suggests either that the cosmological principle is wrong and the universe has preferred directions, or we live in an extraordinarily special location where local geometry happens to align with cosmic features, or there is some unknown foreground or analysis issue that multiple careful studies have all missed. Yet another anomaly is the hemispherical asymmetry. The cosmic microwave background should look statistically identical in all directions. On average, one hemisphere of the sky should have the same temperature, the same fluctuations, the same correlations as the opposite hemisphere. But measurements show a slight asymmetry. One hemisphere has slightly larger temperature fluctuations than the other. The difference is small, only a few percent, but it is statistically significant and reproducible. The axis that divides the asymmetric hemispheres points in a particular direction that happens to align with other anomalies, including the axis of evil. Inflation predicts a perfectly isotropic universe. Temperature fluctuations should be the same everywhere. Finding a hemispheric asymmetry violates this prediction. Where could such asymmetry come from? One possibility is that inflation itself was not perfectly uniform. Perhaps the inflaton field, the quantum field that drove inflation, had gradients across space. Different regions inflated at slightly different rates or for slightly different durations. This would create asymmetries that persisted into the matter distribution and the cosmic microwave background. Testing this requires more complex inflation models than the simple single-field inflation usually assumed. Another possibility is that our observable universe is not representative of the whole universe. Perhaps we see only a small patch of a much larger cosmos. That patch might have special properties that the whole universe does not share. The hemispherical asymmetry might reflect a gradient or boundary condition at the edge of the patch. Beyond our observation horizon, the universe might be quite different. This sounds speculative, but is actually consistent with eternal inflation. Different bubble universes can have different properties. Perhaps we observe a transition region between one bubble's properties and another's. Or perhaps the asymmetries tell us about something that happened to our universe after inflation. If bubble universes collided, those collisions would create asymmetries. The collision would heat one side of our bubble more than the other. This could produce exactly the kind of hemispherical asymmetry we observe. The direction of the asymmetry would point toward where the collision occurred. The magnitude of the asymmetry would depend on the collision's energy and geometry. This explanation connects multiple anomalies. The cold spot could be one collision signature. The hemispherical asymmetry could be another. The axis of evil might point toward the collision direction. Everything would fit together into a coherent picture of a universe that touched others and bears the marks of those encounters. Cosmologists debate these possibilities extensively. Some argue the anomalies are just statistical flukes. When you analyze complex data with many degrees of freedom, you will inevitably find some features that appear unusual. We should not overinterpret patterns that might disappear with more data or better analysis. Others argue the anomalies are too persistent and too numerous to dismiss. We keep finding deviations from perfect isotropy in multiple independent ways. This suggests something real is going on. Our models of the early universe are incomplete. Either inflation was more complex than we thought, or post-inflation events affected the cosmic microwave background in ways we have not accounted for. The cosmic microwave background is our most important window into the early universe. It provides our best constraints on cosmological parameters. It tests inflation and structure formation and cosmic geometry with unmatched precision. But it also shows us that something is not perfectly standard. The deviations are subtle. They require careful analysis to detect, but they persist across decades of observations with progressively better instruments. The universe is trying to tell us something through these anomalies. Perhaps that our models need refinement, perhaps that new physics awaits discovery, or perhaps that our universe is not as isolated and ideal as we have assumed. Perhaps the marks of cosmic contact are written across the sky, visible to anyone who looks carefully at the most ancient light we can observe. Galaxies spin, stars orbit around galactic centers, following paths determined by gravity. The more mass inside a star's orbit, the faster that star must move to avoid falling inward. This is basic Newtonian physics applied on cosmic scales. Measure how fast stars move at different distances from a galaxy's center, and you can calculate how mass is distributed throughout that galaxy. Astronomers have done this for thousands of galaxies. The results make no sense. In the 1970s, Vera Rubin and Kent Ford measured rotation speeds in spiral galaxies using spectrography. They observed light from glowing gas clouds at different distances from galactic centers. By measuring Doppler shifts, they determined how fast the gas was moving. The inner regions rotated as expected. Stars and gas near the center moved faster than material farther out, just like planets in our solar system, where inner planets orbit faster than outer planets. But then something strange happened. Beyond the visible disk of stars, rotation speeds did not drop off as they should. They stayed constant or even increased slightly. Gas at the outer edges of galaxies moved just as fast as gas much closer to the center. This violated expectations completely. Most of a galaxy's visible mass is concentrated near the center. Stars thin out dramatically toward the edges. If visible matter was all that existed, rotation speeds should drop significantly in the outer regions. The orbital velocity should decline, following a simple mathematical relationship called Keplerian falloff. Every planet in our solar system follows this pattern. Every satellite orbiting Earth follows this pattern. Basic physics demands it. Yet galaxies did not obey. The implication was unavoidable. Galaxies contained far more mass than we could see. This invisible mass had to be distributed in huge halos extending well beyond the visible disk. The mass could not be ordinary matter made of protons and neutrons because we would detect it through light emission or absorption. It had to be something else, something dark, something that interacted through gravity but not through electromagnetism. Dark matter was born from this crisis in understanding galaxy rotation. For decades, dark matter solved the rotation problem beautifully. Add enough dark matter in the right distribution, and rotation curves flattened exactly as observed. Computer simulations, including dark matter, reproduced galactic properties successfully. Cosmological observations confirmed that the universe contained far more dark matter than ordinary matter. The cosmic microwave background, gravitational lensing, galaxy clustering, all pointed to the same conclusion. Dark matter existed. It made up about 85% of all matter. The rotation curve problem seemed solved, except dark matter has never been detected directly, despite decades of searching. Experiments deep underground look for dark matter particles interacting with ordinary matter. They find nothing. particle accelerators search for evidence of dark matter production in high-energy collisions. They find nothing. Every attempt to directly observe or create dark matter particles has failed. We infer its existence from gravitational effects, but we know nothing else about it with certainty. Not what particles compose it, not how those particles interact beyond gravity. Nothing. This bothers some physicists enough that they propose alternatives. What if dark matter does not exist? What if gravity works differently than general relativity predicts on galactic scales? Modified Newtonian dynamics, known as MOND, proposes that gravitational acceleration behaves differently when it becomes very weak, as it does in the outer regions of galaxies. Instead of declining smoothly with distance according to Newton's inverse square law, gravity transitions to a different regime where acceleration depends on mass in a new way. This modified gravity produces flat rotation curves without requiring dark matter. MOND works remarkably well for many galaxies. It predicts rotation curves that match observations better than dark matter in some cases. It explains relationships between visible matter and rotation speeds that seem puzzling in dark matter models. For individual galaxies, MOND often outperforms dark matter, but MOND fails on larger scales. It cannot explain gravitational lensing by galaxy clusters. It struggles with the cosmic microwave background. It does not naturally fit into a cosmological framework the way dark matter does. Most physicists reject MOND for these reasons, despite its success with galaxy rotation. Yet the rotation curve problem has not entirely gone away even with dark matter. Detailed observations reveal discrepancies between predicted and observed rotation curves that persist even after adding dark matter halos. The cores of some galaxies rotate differently than simulations predict. The relationship between dark matter distribution and visible matter distribution does not always match simulations. Small irregularities in rotation curves hint at structure in dark matter halos that we do not understand. More troubling are galaxies that seem to have little or no dark matter. In 2018, astronomers discovered NGC 1052-DF2, a diffuse galaxy with rotation speeds indicating it contained almost no dark matter. This should not exist. Galaxies are supposed to form within dark matter halos. A galaxy without dark matter is like finding a planet with no core. It challenges our entire picture of galaxy formation. Since then, other galaxies with anomalously low dark matter have been found. Not many, but enough to create a puzzle. If dark matter is fundamental to galaxy formation, why do some galaxies lack it? These ultra-diffuse galaxies might have had their dark matter stripped away through tidal interactions with larger galaxies, or they might have formed through unusual processes that concentrated visible matter without much dark matter. But explaining them requires special circumstances that seem contrived. Why would nature produce galaxies spanning the full range from dark matter dominated to, essentially, no dark matter? Standard formation models do not predict such variety. Then there are galaxies with too much dark matter. Some dwarf galaxies have rotation curves indicating extremely high dark matter concentrations. The ratio of dark matter to visible matter exceeds what simulations predict. These galaxies appear almost entirely composed of dark matter, with just a tiny amount of visible matter embedded in enormous dark halos. Again, special explanations can account for individual cases. But the range of dark matter content observed in galaxies is wider than models comfortably produce. The distribution of dark matter within galaxies also shows anomalies. Simulations predict that dark matter density should increase steeply toward galactic centers, following what is called an NFW profile, named after the researchers who first described it. But observations often show flatter central density profiles. Dark matter appears more smoothly distributed than simulations predict. This is called the core cusp problem. Simulations produce cusps sharp central peaks in dark matter density. Observations show cores, flatter central regions. The discrepancy has persisted for 2 decades, despite improvements in both simulations and observations. Various solutions have been proposed. Perhaps dark matter interacts with itself in ways that redistribute it from cuspy to flat profiles. Perhaps supernova explosions blow dark matter out of galactic centers. Perhaps the first generations of stars created feedback that affected dark matter distribution. Each solution works for some galaxies, but not all. The core cusp problem remains unresolved. We do not fully understand how dark matter is distributed, even if we accept that it exists. All of this suggests our picture of galaxies is incomplete. Either dark matter is more complex than simple non-interacting particles, or our understanding of how it distributes itself is wrong, or something else beyond dark matter affects galactic dynamics. Some researchers propose that modified gravity and dark matter might both be needed. Perhaps general relativity requires modification on galactic scales even if dark matter exists. Perhaps the true theory of gravity includes corrections that become important in certain regimes. Perhaps we are seeing effects from extra dimensions or quantum gravity that manifest in how galaxies rotate. Or perhaps the anomalies tell us that galaxies are influenced by more than just the matter and dark matter we can directly account for. If our universe is close to other universes in higher dimensional space, gravitational effects could leak between them. Dark matter in neighboring universes might gravitationally affect galaxies in our universe. This would appear as extra mass that we cannot see or detect directly because it exists in another reality. The effects would be strongest where the universes are closest in whatever extra dimensions separate them. This might explain why some galaxies have strange dark matter distributions. They are feeling gravitational pull from matter that is not in our universe at all. This idea is highly speculative. Most physicists do not take it seriously. But the persistence of galactic rotation anomalies, despite decades of effort to resolve them, suggests something fundamental is missing from our models. Dark matter solves many problems, but creates new ones. Modified gravity works in some contexts, but fails in others. Perhaps the answer requires thinking beyond our universe entirely. Perhaps the strange behavior of galaxies, the unexpected rotation curves, the anomalous dark matter distributions all point toward influences from hidden realities that make their presence felt through gravity, even though they remain forever invisible to our telescopes. The universe should look the same in all directions. This is the cosmological principle, the foundation of modern cosmology. On the largest scales, after averaging over local irregularities like galaxies and clusters, matter should be distributed uniformly. The laws of physics should work the same everywhere. Space should expand at the same rate in all directions. The universe should be isotropic, the same everywhere you look, and homogeneous, the same at every location. This principle is not just convenient assumption, it is testable prediction, and the tests keep showing that something is wrong. The cosmic microwave background provides the cleanest test of isotropy. This radiation comes from every direction, from the edge of the observable universe. If the universe is isotropic, the temperature should be the same in all directions after accounting for our motion through space. Our solar system moves relative to the cosmic reference frame at about 370 kilometers per second. This motion creates a dipole pattern in the cosmic microwave background. One direction appears slightly hotter because we are moving toward it, blue shifting the radiation. The opposite direction appears cooler because we are moving away, red shifting the radiation. This dipole has been measured precisely. After subtracting it, the cosmic microwave background should show no other large-scale directional patterns. But it does. Multiple studies have found that even after removing the motion dipole, residual asymmetries remain. The hemispherical asymmetry we discussed earlier shows that one half of the sky has slightly stronger temperature fluctuations than the other half. This should not exist in an isotropic universe. The alignment of the quadrupole and octupole creates preferred directions that should not exist. The cold spot represents a localized but extreme deviation from uniformity. Each anomaly individually might be dismissed as statistical fluctuation or undetected systematic error. Together they paint a picture of a universe that is not perfectly isotropic. The fine structure constant might vary across the universe. This is one of the fundamental constants of nature, determining the strength of electromagnetic interactions. It appears in countless physical formulas and is supposed to be constant everywhere and everywhen. Yet observations of distant quasars suggest the fine structure constant might have different values in different directions. John Webb and his team have analysed light from hundreds of quasars, looking at absorption lines created by gas clouds between us and the quasars. The wavelengths of these absorption lines depend sensitively on the fine structure constant. Measurements show hints that the constant is slightly different in different parts of the sky. If confirmed, this would be revolutionary. Fundamental constants are supposed to be fundamental. They should not vary with location. Finding spatial variation in the fine structure constant would shatter our understanding of physics. It would mean the universe is not just lopsided in how matter is distributed, but in its basic physical laws. Different regions of space would have slightly different physics. Chemistry would work differently. Stars would burn at different rates. Everything would change. The results remain controversial. Other teams analysing similar data find no evidence for variation. The signal is subtle, close to observational limits. Systematic errors in measuring quasars' absorption lines could create spurious signals that look like varying constants. Most physicists remain skeptical, but if the variation is real, it points toward a universe more complex than the standard model allows. Perhaps different bubble universes in the multiverse have different physical constants. Perhaps we observe regions influenced by nearby bubbles where the constants transition between different values. Perhaps what we see as variation is actually evidence of cosmic boundaries or interfaces. Galaxy distributions show other hints of asymmetry. The dark flow we discussed points matter preferentially in one direction. This creates a large-scale anisotropy in galaxy motions. Surveys of galaxy clustering find that structure is not quite uniform when analysed carefully. Some directions have slightly more clustering than others. Some regions appear more evolved, with older galaxy populations and more merged structures. Others appear younger and less evolved. These differences are subtle but persistent. The Hubble constant might vary with direction. Some measurements suggest the expansion rate is not quite the same when looking at galaxies in different parts of the sky. This would be extraordinary. Cosmic expansion should be uniform. Space should stretch equally in all directions. Finding directional variation would indicate fundamental anisotropy in how the universe expands. Most measurements find no significant directional variation, but a few studies report hints of anisotropy at levels just above observational uncertainties. More data is needed to determine whether these hints are real or statistical noise. The simplest explanation for all these anomalies is that they are coincidences. We are seeing patterns in noise. We are finding false signals due to undetected systematic errors. The universe really is isotropic and homogeneous. We just have not proven it yet with sufficient precision. As observations improve and datasets grow, the anomalies will disappear. This is the conservative view held by most cosmologists. The cosmological principle has been tested extensively and passed most tests. A few marginal anomalies should not overturn decades of successful theory. But what if the anomalies are real? What could cause large-scale anisotropy? One possibility is that the universe is rotating. If space itself rotates, it would create preferred directions and asymmetries in structure formation. General relativity allows rotating universes. But observations constrain cosmic rotation to extremely slow rates. Any rotation must be so slow that it produces negligible effects. It cannot explain the observed anomalies without being faster than observations allow. Another possibility is that the universe has non-trivial topology. Perhaps space wraps around and connects to itself in complex ways. A universe with unusual topology could create apparent asymmetries because we would see the same structures multiple times in different directions. This could produce correlations and patterns that violate naive expectations of isotropy. Astronomers have searched for such topological signatures by looking for repeated patterns in galaxy distributions or the cosmic microwave background. No convincing evidence has been found. If the universe has interesting topology, the scale is larger than we can currently observe, or perhaps the universe underwent phase transitions that broke symmetries. During the first moments after the Big Bang, the universe was extremely hot. As it cooled, it underwent transitions analogous to water freezing into ice. These transitions can spontaneously break symmetries, creating preferred directions or domains with different properties. If such transitions occurred, their effects might persist as large-scale asymmetries today. This is theoretically possible, but requires specific particle physics beyond the standard model. No independent evidence supports the necessary particle physics. Then there are explanations involving the multiverse. If our universe is one bubble among many, interactions with other bubbles during early cosmic history could create asymmetries. Each collision would preferentially affect one direction. Multiple collisions from different directions might create a complex pattern of anisotropies. The hemisphere that collided with another bubble would evolve differently than the opposite hemisphere. The cold spot could be one collision signature, the hemispherical asymmetry another. The axis of evil might point toward where multiple collisions occurred. This explanation naturally produces the kinds of anomalies we observe without requiring fine-tuning or special conditions. Alternatively, gravitational influence from beyond our cosmic horizon could create anisotropies. Inflations stretch space so rapidly that regions now beyond our observation limit were once close enough to affect each other. Enormous mass concentrations just beyond the horizon might gravitationally pull matter in our observable universe, creating flows and asymmetries. This does not require other universes, just a universe larger than what we can see. But the mathematics of inflation make this difficult. Structures large enough to create observed effects should not exist because inflation smoothed everything out. Invoking such structures requires either that inflation was incomplete or that something after inflation created enormous concentrations beyond our horizon. What seems clear is that the universe is not as perfectly symmetric as the cosmological principle demands. The deviations are small. None violate the principle so dramatically that we must abandon it, but they accumulate. The cosmic microwave background shows asymmetries. Galaxy motions show flows. Structure shows alignments. Physical constants might vary. Expansion might be directional. Each measurement pushes against the assumption of perfect isotropy. Perhaps the universe is only approximately isotropic. Perhaps the cosmological principle is a good approximation, but not exact truth. Perhaps on the very largest scales, scales comparable to the observable universe itself, symmetry breaks down. And perhaps this breaking is evidence of influences from beyond, from other realities touching ours, and leaving marks that we interpret as a universe that is slightly, stubbornly, persistently lopsided. The universe is expanding faster and faster. This should not be happening. Gravity should slow the expansion. Every piece of matter in the universe gravitationally attracts every other piece. This attraction should act as a cosmic brake, gradually slowing the expansion rate over time. Eventually, gravity might even stop the expansion entirely and cause the universe to collapse back on itself in a big crunch. This was the expectation from general relativity and basic physics. Then in 1998, two teams of astronomers measuring distant supernovae discovered something shocking. The expansion was not slowing down, it was speeding up. The discovery came from studying Type Ia supernovae. These stellar explosions occur when white dwarf stars accumulate too much mass and explode catastrophically. The physics of the explosion is similar for all Type Ia supernovae, making them standard candles. Their intrinsic brightness is known. Measure how bright they appear from Earth, and you can calculate their distance. Compare that distance to their redshift, how much their light has been stretched by cosmic expansion, and you determine the expansion history of the universe. The two teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, independently measured dozens of distant supernovae. They expected to find that expansion was slowing. Instead, they found that distant supernovae were fainter than expected, indicating they were farther away than their redshifts suggested. Space had expanded more than it should have between the time the supernova exploded and now. This meant expansion was accelerating. Something was pushing space to expand faster and faster over time. The teams checked their results exhaustively. They looked for systematic errors. They searched for alternative explanations. The conclusion remained inescapable. Cosmic acceleration was real. This discovery revolutionized cosmology and earned the team leaders the Nobel Prize in Physics. But it also created a massive problem. What was causing the acceleration? Gravity could not do it. Gravity only attracts. You need something with negative pressure, something that pushes rather than pulls to accelerate cosmic expansion. Physicists called this mysterious something dark energy. The name captured our profound ignorance about what it was. Dark meaning invisible, energy meaning it had energy density, but beyond that, nothing was known. The simplest candidate for dark energy is the cosmological constant. Einstein introduced this into his equations of general relativity as a way to create a static universe that neither expanded nor contracted. When Hubble discovered cosmic expansion, Einstein abandoned the cosmological constant, supposedly calling it his greatest blunder. But the constant never really went away. Quantum field theory predicts that empty space should have energy. Virtual particles constantly appear and disappear in the vacuum. These quantum fluctuations contribute to the energy density of space itself. This vacuum energy acts exactly like a cosmological constant, creating negative pressure that drives accelerating expansion. The problem is the magnitude. Quantum field theory can calculate how much vacuum energy should exist. The calculation gives an answer approximately 10 to the power of 120 times larger than observations allow. This is not a small discrepancy. This is the worst prediction in the history of physics, off by more than 100 orders of magnitude. Something is catastrophically wrong with either the calculation or our understanding of how quantum fields behave in curved space-time. Physicists have struggled with this vacuum energy problem for decades without resolution. Various alternatives to the cosmological constant have been proposed. Maybe dark energy is not constant, but changes with time. Maybe it is a new quantum field with specific properties that create the observed acceleration without the vacuum energy problem. These dynamical dark energy models have names like quintessence, phantom energy, K-essence. Each requires new physics beyond the standard models of particle physics and cosmology. Each must be carefully tuned to match observations without creating conflicts with other well-established facts. None have gained widespread acceptance because none are clearly better than the simple cosmological constant at explaining observations. Some physicists question whether dark energy exists at all. Perhaps we are misinterpreting the supernova data. Perhaps type Ia supernovae are not as uniform as we assume. Perhaps their brightness evolves with cosmic time or depends on their environment in ways we have not accounted for. Extensive studies of supernova properties find no evidence for such evolution. Hundreds of supernovae, measured by multiple independent teams, all tell the same story. Acceleration is real. Alternatives to dark energy seem increasingly contrived. Modified gravity offers another approach. Perhaps general relativity breaks down on cosmic scales. Perhaps gravity becomes repulsive rather than attractive when averaged over billions of light years. Many modified gravity theories have been constructed. Some can reproduce cosmic acceleration without requiring dark energy, but most fail other tests. They cannot simultaneously explain galaxy rotation curves, gravitational lensing, the cosmic microwave background, and large-scale structure. The standard model with dark energy passes all these tests, even though we do not understand what dark energy is. Measurements of cosmic acceleration have become increasingly precise. Observations now show that dark energy makes up about 68% of the total energy density of the universe. Dark matter contributes about 27%. Ordinary matter, everything we see, including stars, planets, gas, dust, everything made of atoms, contributes only about 5%. We live in a universe dominated by things we do not understand. Dark energy is the largest component, but the most mysterious. We have no idea what it is. We just know it exists because of what it does to cosmic expansion. The discovery of acceleration also created tension with the age of the universe. If expansion was always accelerating, the universe is older than if expansion was decelerating. This affects calculations of when the first stars formed, when galaxies assembled, when structure emerged. Some of these ages came into conflict with independent estimates from stellar evolution and radioactive dating. The conflicts have been mostly resolved as measurements improved, but they highlight how sensitive cosmology is to the expansion history. Dark energy might connect to other mysteries. Some theories propose that dark energy and dark matter are related, two aspects of a single underlying phenomenon. Others suggest dark energy is connected to the vacuum structure of space-time itself, perhaps related to quantum gravity or extra dimensions. If our universe exists in higher dimensional space alongside other universes, dark energy might represent interaction between branes or leakage of gravity from parallel realities. These ideas remain speculative, but illustrate how dark energy might be a clue to physics beyond what we currently understand. The acceleration could also vary across the universe. If dark energy is not perfectly uniform, some regions would expand faster than others. This would create anisotropies that could be detected through careful observations. Several studies have searched for evidence of varying dark energy. Most find that dark energy appears uniform within measurement uncertainties. But if future observations detect variation, it would transform our understanding. It might indicate that dark energy is more complex than a simple constant. It might reveal structure in whatever field or mechanism drives acceleration. Or it might reveal that acceleration is not caused by dark energy at all, but by influences from other universes. If multiple bubble universes exist, their relative motions or gravitational interactions could affect how space expands in each bubble. From inside one bubble, this would appear as mysterious acceleration that we attribute to dark energy. The acceleration would actually be caused by the configuration and evolution of the larger multiverse. We would be measuring something real, but interpreting it in terms of local physics when the cause is extra-dimensional. This would explain why dark energy is so difficult to understand. It is not a property of our universe alone, but of how our universe relates to others. The mystery of cosmic acceleration remains one of the most profound puzzles in modern physics. We know acceleration is real. We have measured it precisely using multiple independent methods. But we have no satisfying explanation for what causes it. Dark energy is a name for our ignorance, not an answer. Every theoretical attempt to explain it either predicts the wrong magnitude by absurd factors or requires fine-tuning that seems unnatural. Perhaps the answer requires thinking beyond our universe. Perhaps what we call dark energy is really evidence that our reality is not isolated, that it touches and interacts with others, that the acceleration we measure reflects influences from hidden realities making themselves known through the expansion of space across billions of light years and billions of years of cosmic time. Why now? This question haunts cosmologists studying dark energy. For most of cosmic history, the universe was matter-dominated. The expansion rate was determined primarily by how much matter existed. Dark energy was there, its density constant over time, as the name cosmological constant suggests. But it contributed negligibly to the total energy budget. Matter density decreased as the universe expanded, diluting as space grew. But dark energy density remained constant, the same in every cubic meter of space, regardless of expansion. Eventually, as matter thinned out, dark energy came to dominate. That transition happened relatively recently in cosmic history, only about 5 billion years ago. This seems like an incredible coincidence. The universe is 13.8 billion years old. For the first 9 billion years, matter dominated. For the last 5 billion years, dark energy has dominated. We happen to live in the brief cosmic epoch when these two components have comparable densities. Why should we exist at this special time? The probability seems extremely small. Dark energy and matter have completely different properties. Their densities evolve differently as the universe expands. Yet they happen to be comparable right now, during the era when intelligent observers exist to notice. This is called the coincidence problem. The issue becomes even more striking when you consider the future. Dark energy density stays constant while matter density continues to decrease. In 1 trillion years, matter will be so diluted that dark energy will dominate completely. The universe will be empty and dark, expanding exponentially, with galaxies too far apart to see each other. Any observers in that far future would measure an energy budget almost entirely composed of dark energy, with matter contributing negligibly. Conversely, if intelligent life had emerged much earlier in cosmic history, say 2 billion years after the Big Bang, those observers would see a matter-dominated universe with dark energy barely detectable. The cosmic energy budget changes dramatically over time. We live during the narrow window, when both matter and dark energy are important. Why? Is it coincidence? Are we just lucky to exist when we do? Or does our existence at this time tell us something deep about the universe? This connects to anthropic reasoning, the idea that we must observe a universe compatible with our existence. If the cosmic energy budget needed to be approximately balanced between matter and dark energy for life to emerge, then obviously we observe it balanced, because we could not exist otherwise. But why would life require this balance? Structure formation depends on matter density, not on the ratio of matter to dark energy. Stars form, planets cool, chemistry develops based on matter and radiation, not dark energy. Dark energy only becomes important on enormous scales, affecting cosmic expansion, but not local physics. Some cosmologists argue the coincidence is not as extreme as it appears. The transition from matter domination to dark energy domination had to happen sometime. We happen to observe the universe a few billion years after that transition. Civilization emerged relatively early in cosmic history from a certain perspective. Stars will continue forming for trillions of years. Most planets that will ever exist have not yet formed. We are actually quite early in the universe's potential for hosting life, not late. By that reasoning, seeing matter and dark energy with comparable densities is not too surprising. We could have emerged earlier when matter dominated more strongly, or later when dark energy dominated more strongly. But we happen to be here now. But the coincidence problem is quantitatively troubling. The density of matter has decreased by a factor of billions since the Big Bang. The density of dark energy has remained constant. These two numbers, evolving in completely independent ways, happen to be within a factor of 2 of each other right now. If we appeared even 1 billion years earlier, matter would dominate by a factor of several. 1 billion years later, dark energy would dominate by a factor of several. The window, when they are truly comparable, is narrow, perhaps only a couple billion years wide. The age of the universe is 13.8 billion years. Finding ourselves in that narrow 2 billion year window seems improbably lucky. Alternative explanations involve modifying dark energy. If dark energy is not constant but instead evolves with time in a specific way, perhaps the coincidence can be explained. Maybe dark energy remained negligible for most of cosmic history and only recently became important because of some physical process. This would mean we do not happen to observe the universe at a special time. Rather, dark energy became important precisely when the universe reached the age it now has. This requires dark energy to have specific properties beyond a simple cosmological constant. It must be dynamical, changing based on some mechanism that kicks in at a particular cosmic epoch. Many such models have been constructed. None are clearly better than the cosmological constant at matching observations. Another approach invokes the multiverse. If countless universes exist with different dark energy densities, most would be inhospitable to life. Universes with too much dark energy would expand so rapidly that structure could never form. Gravity would be unable to pull matter together against the accelerating expansion. No galaxies, no stars, no planets, no life. Universes with negative dark energy density would collapse too quickly. Again, no time for structure to develop. Only universes with dark energy density in a narrow range would allow the billions of years needed for stars to form, heavy elements to be created, planets to cool, and life to emerge. We necessarily find ourselves in one of those rare universes because we could not exist in the others. The apparent coincidence is selection bias. We observe dark energy comparable to matter density because that is what life-permitting universes look like. This anthropic explanation is unsatisfying to many physicists. It abandons the goal of calculating dark energy density from first principles. It says we observe what we observe because we must, but it does not explain why the multiverse exists or why different universes have different dark energy. It simply pushes the mystery back one level. Why is there a multiverse? Why does dark energy vary between universes? These questions remain unanswered. Some researchers suggest the coincidence is telling us something about the relationship between matter and dark energy. Perhaps they are not independent. Perhaps dark energy is created by matter in some way. This would naturally explain why they have comparable densities during certain cosmic epochs. When matter reaches a specific density, it triggers dark energy to activate or change properties. This sounds far-fetched, but variations of this idea have been explored. Maybe dark energy couples to matter through unknown fields. Maybe the vacuum energy adjusts itself based on matter density. These models require new physics and careful construction to avoid contradicting observations. Or perhaps the coincidence points to influences from other universes. If our universe is interacting with nearby parallel realities, those interactions might affect dark energy. The apparent acceleration we observe might not be caused by vacuum energy inherent in our universe, but by gravitational effects from matter and energy in other universes. The strength of these effects would depend on how close other universes are, in whatever extra dimensions separate them. Perhaps the closeness changes over time as universes move relative to each other in higher dimensional space. The transition to dark energy domination might reflect a change in the multiverse configuration rather than evolution of dark energy itself. We would measure this as dark energy density becoming important at a specific time, creating the apparent coincidence. The coincidence problem remains unsolved. We live during a special cosmic epoch when matter and dark energy have comparable importance. This could be luck, selection bias, or evidence that our understanding is incomplete. Combined with all the other mysteries, the unknown nature of dark energy, the Hubble tension, the strange motions of galaxies, the impossible structures, the coincidence adds to the sense that something fundamental is missing from our cosmological models. The universe seems to be assembled in a way that defies simple explanation. Every measurement reveals new puzzles. Every advance in understanding raises new questions. We have mapped billions of galaxies across cosmic history. We have measured expansion with extraordinary precision. Yet the more we learn, the more we realize how much remains unexplained. And perhaps the explanations, when they come, will require us to think beyond our universe entirely. Astronomers are not giving up. The accumulation of anomalies has spurred an explosion of new observations and experiments designed to test cosmological models more rigorously than ever before. Multiple large-scale surveys are mapping the universe in unprecedented detail. New telescopes on the ground and in space are pushing observational limits. Theoretical physicists are exploring alternatives to the standard model, seeking modifications that could explain the anomalies without breaking everything that works. The next decade will bring a flood of new data that should clarify which anomalies are real and which are measurement artifacts or statistical fluctuations. The Vera Rubin Observatory in Chile will soon begin the legacy survey of space and time. This decade-long project will photograph the entire southern sky every few nights, creating the most detailed movie of the changing universe ever made. The observatory's massive camera will detect billions of galaxies. It will catalogue supernovae, map gravitational lensing, trace the growth of structure, measure galaxy clustering with unprecedented precision. Any large-scale asymmetries or anomalies in galaxy distributions will stand out clearly in this enormous dataset. The Rubin Observatory will either confirm that the universe is uniform and isotropic as the standard model predicts, or it will reveal deviations that demand new physics. The Euclid Space Telescope, launched by the European Space Agency, is mapping the geometry of the universe by measuring the shapes and positions of billions of galaxies. Gravitational lensing, the bending of light by mass, distorts galaxy images in subtle ways. Measuring these distortions reveals where dark matter is located and how structure has grown over cosmic time. Euclid will constrain dark energy properties more tightly than ever before. It will test whether dark energy is truly constant or evolves with time. It will search for evidence that gravity works differently on cosmic scales than general relativity predicts. NASA's Nancy Grace Roman Space Telescope will complement Euclid with infrared observations. Launching in the mid-2020s, Roman will measure distances to hundreds of millions of galaxies using multiple techniques. It will trace the expansion history of the universe with precision that should finally resolve the Hubble tension. Either the early universe measurements or the local measurements will be shown to be wrong, or we will confirm that the tension is real and requires new physics to explain. Roman will also map dark matter through gravitational lensing and study the properties of dark energy across cosmic time. Ground-based surveys are also advancing. The Dark Energy Spectroscopic Instrument on the Mail Telescope in Arizona is measuring spectra of tens of millions of galaxies and quasars. Spectroscopy reveals precise redshifts and allows detailed study of how structure has grown. DeSci will test cosmological models by measuring baryon acoustic oscillations, subtle patterns in galaxy clustering left over from sound waves in the early universe. These patterns provide a standard ruler for cosmology, allowing precise measurement of the expansion history. If anomalies exist in how structure grew or how expansion evolved, DeSci should detect them. The Square Kilometre Array, a massive radio telescope being built in Australia and South Africa, will map hydrogen gas throughout the universe. Hydrogen emits radio waves at a specific frequency. Measuring hydrogen distributions traces matter that is otherwise invisible. The SKA will study the cosmic web in unprecedented detail, revealing how matter flows along filaments and accretes into galaxies. It will search for any large-scale flows like the dark flow by measuring galaxy motions across enormous volumes of space. CMBS-4, the next-generation cosmic microwave background experiment, will map the ancient light with exquisite precision. Deploying in the late 2020s at multiple sites in Antarctica and Chile, CMBS-4 will measure temperature and polarization fluctuations across the sky at levels limited only by fundamental astrophysical foregrounds. It will search for signatures of inflation, test for primordial gravitational waves, constrain the number of neutrino species, and look for any deviations from perfect isotropy. If the cosmic microwave background contains hidden patterns or asymmetries, CMBS-4 will find them. Gravitational wave observatories offer another window into the cosmos. LIGO and Virgo detect waves from merging black holes and neutron stars. These observations provide independent measurements of cosmic expansion by comparing gravitational wave luminosity distances to electromagnetic redshifts. Future detectors like the Einstein Telescope and Cosmic Explorer will dramatically increase sensitivity. The Laser Interferometer space antenna, launching in the 30s, will detect low-frequency gravitational waves from massive black hole mergers and possibly from cosmic strings or other exotic early universe phenomena. If bubble universe collisions occurred, they might have produced gravitational waves detectable by LIS. Particle physics experiments search for dark matter directly. Detectors deep underground wait for dark matter particles to interact with ordinary matter. So far, no convincing signal has been found, but new experiments with improved sensitivity continue the search. If dark matter is detected and its properties measured, this would constrain cosmological models enormously. We would finally know what dark matter is rather than just inferring its existence from gravity. Theorists are also making progress. Improved computer simulations with higher resolution and better physics are testing whether standard cosmological models can reproduce observed structures. Some recent simulations have reduced discrepancies between predictions and observations for problems like the missing satellites. Perhaps the issues are not fundamental failures, but artifacts of limited simulation resolution or incomplete modelling of complex gas physics and star formation. As simulations improve, they either converge with observations, confirming the standard model works, or the discrepancies persist, confirming new physics is needed. Alternative theories are being developed. Modified gravity theories like M-ONDI are being extended to work on cosmological scales. New dark energy models with specific time evolution are being tested against observations. Ideas involving extra dimensions, varying constants, quantum gravity effects, all are being explored. Each theoretical proposal makes predictions that can be tested against the flood of incoming data. The next decade will separate viable alternatives from dead ends. Some researchers are thinking even more radically. What if the universe is not what it appears? What if we are misinterpreting fundamental observations? Some propose that cosmic acceleration is an illusion created by our special location in an underdense region. Others suggest that light propagation through the universe is affected by inhomogeneities in ways we have not properly accounted for. Still others explore whether quantum mechanics on cosmic scales might create effects that mimic dark energy. These ideas are controversial but worth investigating given the depth of our confusion about dark energy and cosmic expansion. The multiverse hypothesis is also being tested indirectly. If eternal inflation produces bubble universes, collisions between bubbles should leave detectable marks. Searches of the cosmic microwave background look for circular patterns with specific properties predicted by collision models. So far, no definitive signals have been found beyond the cold spot, but analyses continue with increasingly sophisticated methods. Future CMB data might reveal additional collision signatures or rule them out entirely. What seems certain is that answers are coming. The observational programs now underway will map the universe in such detail that anomalies cannot hide. If the dark flow is real, future surveys will confirm it beyond doubt or show it was a statistical fluke. If galaxy alignments exist, larger data sets will make the patterns unmistakable or show they were selection effects. If the Hubble tension persists with better data, we will know the standard model is incomplete and must be modified. If impossible structures continue to appear, we will be forced to revise our understanding of structure formation. Within the next decade or two, cosmology will enter a new era. Either the standard model will be vindicated, its apparent problems shown to be measurement issues or statistical fluctuations, and we will understand with confidence that our universe is well described by general relativity plus dark matter plus dark energy. Or the standard model will fail definitively, unable to account for robust observations, and we will know that new physics awaits discovery. That new physics might involve modifications to gravity, new properties of dark matter or dark energy, extra dimensions, or influences from beyond our universe. Whatever the answer, it will come from careful observation and rigorous testing. We have found billions of galaxies. Something is off. Now we are finding out what. Imagine the confirmation arrives. A future space telescope maps the cosmic microwave background with such precision that multiple bubble collision signatures become unmistakable. Or gravitational wave detectors find the specific pattern of primordial waves predicted by early universe collisions. Or galaxy surveys reveal asymmetries so extreme and systematic that conventional physics cannot explain them. The evidence accumulates until the conclusion becomes unavoidable. Our universe is not isolated. Other realities exist beyond our cosmic horizon, and they have touched ours. They perhaps continue to touch us even now. What would this mean? The philosophical implications would be staggering. Humanity has always wondered whether we are alone in the cosmos. The discovery of microbial life on Mars or chemical signatures of life in exoplanet atmospheres would revolutionize biology and shift our perspective on life's ubiquity. But discovering other universes would be more profound. It would mean reality is vastly larger than anything we imagined. Not just more space containing more galaxies and possibly more life, but other realms with potentially different laws of physics, different particles, different forces. The multiverse would be real. Our universe would be one bubble in an infinite foam of universes. Everything we can observe, all 2 trillion galaxies scattered across 93 billion light-years, would be revealed as a tiny fraction of total existence. This realization would fundamentally change how we think about our place in reality. The Copernican principle would extend to its ultimate conclusion. Not only is Earth not the center of the solar system, and the solar system not the center of the galaxy, and the galaxy not the center of the universe, but our universe itself would not be the center of anything. We would be citizens of one bubble among infinite bubbles, observing local conditions, while the greater multiverse extends beyond all possibility of observation or interaction. The religious and spiritual implications would be debated for generations. Some would see the multiverse as evidence of divine creativity, a cosmos so vast and varied that it reflects infinite imagination. Others would argue that a creator is unnecessary in a multiverse where all possibilities exist by necessity. If the multiverse is eternal and infinite, producing all possible configurations, then our apparently fine-tuned universe is inevitable. No design required. The debate between theism and naturalism would continue, but in a new context where both sides claim the multiverse supports their position. The scientific implications would be immediate and practical. Confirming the multiverse would validate inflation theory and extend our confidence in physics to the earliest moments after the Big Bang. It would demonstrate that general relativity and quantum mechanics, properly understood, describe not just our universe, but a much larger structure. This would guide efforts to develop quantum gravity and unified theories. If the multiverse emerges naturally from correct physics, then that physics must be capable of producing eternal inflation and bubble nucleation. Theories like string theory that predict this behavior would gain support. Theories that cannot accommodate a multiverse would face challenges. But confirming the multiverse would also create new scientific questions, more challenging than those we face now. If other universes have different physical constants, can we predict the distribution of those constants across the multiverse? If we can observe collision signatures, can we learn anything about the properties of the universes we collided with? Do collisions happen randomly, or are there patterns that tell us about multiverse structure? Could we ever detect more than just collision scars? Might there be other ways that universes influence each other that we have not considered? The answer to that last question might be yes. If universes can collide, perhaps they can interact in other ways. Gravitational influence across extra dimensions might affect cosmic expansion, galaxy formation, or fundamental constants in our universe. Dark matter might exist partly in other universes, its gravitational effects leaking into ours. Dark energy might represent the pressure from other universes pushing against ours through higher dimensional space. The anomalies we observe, all the strange behaviors of galaxies and cosmic expansion, might be evidence of ongoing interaction rather than ancient collisions. We would not be isolated, but embedded in a dynamic multiverse where influences flow between realities constantly. This could explain fine-tuning in a new way. Perhaps the constants in our universe are affected by proximity to other universes. Perhaps they vary slightly across our universe because different regions are closer to different neighbours in the extra dimensions. The fine-tuning would still be selection bias. We exist in a universe with life-permitting constants because we could not exist otherwise. But the mechanism would be different. Instead of our bubble happening to nucleate with the right constants randomly, perhaps interactions with neighbouring bubbles pushed our constants into life-permitting ranges through dynamical processes we do not yet understand. Technology could potentially benefit, though this is highly speculative. If we understand how universes interact, could we manipulate those interactions? Could we affect local physical constants in controlled ways by altering the geometry of our universe's interface with others? This sounds like pure science fiction, but if our universe truly touches others and exchanges influence, studying that interface might teach us principles that lead to technologies we cannot currently imagine. At minimum, understanding the full context of our universe's place in the multiverse would inform our theories and might inspire new approaches to problems we currently see as fundamental limitations. The discovery would also affect how we think about the future. If eternal inflation continues beyond our bubble, new universes are forming constantly. The multiverse is not static, but growing. In some far future, After our universe has cooled and stars have died, new bubbles will be young and hot, full of possibility. The totality of existence would be eternal, always containing young universes where structure forms and perhaps life emerges. This provides a kind of cosmic optimism. Even as our universe fades, the multiverse renews itself forever. Existence never ends, only transforms. But it would also emphasize our cosmic isolation. If other universes exist but are forever unreachable, we remain fundamentally alone in our bubble. We might observe evidence of their existence. We might measure effects of their influence, but we could never visit them, never communicate with whatever beings might exist there, never share knowledge or experience across the boundary. The multiverse would be real but inaccessible. We would be like prisoners aware that other cells exist but unable to reach them. This might make our universe feel smaller and more precious. Everything we care about, everyone we love, all beauty and meaning, confined to one bubble surrounded by infinite others we can never touch. Yet some physicists speculate that the boundaries might not be absolute. Quantum tunneling might allow particles to jump between nearby universes under extraordinary circumstances. Wormholes might connect different regions of the multiverse if the topology of extra dimensions permits it. Advanced civilizations far in our future might discover ways to manipulate the fabric of reality that we cannot conceive today. Perhaps the isolation is temporary, a limitation of our current technology and understanding, rather than an inherent feature of the multiverse. Perhaps someday, in times almost impossibly distant, beings descended from humanity or from other civilizations in our universe will find ways to reach beyond our bubble and make contact with others. These speculations may be fantasy, but they illustrate how discovering the multiverse would open entirely new directions for thought and inquiry. We would know we are not alone in the largest sense. We would know reality is richer and stranger than we imagined. And we would know that the anomalies we observe, the strange motions of galaxies, the unexpected expansion, the impossible structures, all are clues to this larger truth. Our universe has been trying to tell us something through these puzzles, that it is not isolated, that it touches others, that beyond the observable cosmos lies infinity. We have found billions of galaxies. We have mapped their positions across enormous volumes of space. We have measured their motions, their properties, their distributions. We have traced cosmic structure from the earliest times, visible in the cosmic microwave background, to the present day, 13.8 billion years later. We have observed supernovae, quasars, gravitational waves, and countless other phenomena. We have built theoretical models based on general relativity and quantum mechanics and tested those models against observations. In many ways, our understanding of the universe has become extraordinarily successful. We can explain the cosmic microwave background. We can predict the abundances of elements. We understand star formation and galaxy evolution in impressive detail. But something is off, not one thing, many things. The dark flow suggests matter is moving in ways it should not. The Hubble tension shows we cannot agree on how fast space is expanding. Galaxy rotation curves require dark matter we cannot find. Satellite galaxies are missing or misaligned. Impossible structures span scales too large to have formed. The cosmic microwave background shows anomalies in its largest patterns. The universe appears subtly lopsided rather than perfectly isotropic. Cosmic acceleration demands dark energy we do not understand. The coincidence of matter and dark energy densities seems improbably convenient. Galaxy alignments hint at large-scale correlations that should not exist. Voids are too empty. Physical constants might vary across space. Each anomaly individually could potentially be explained. Measurement error here, statistical fluctuation there, incomplete modeling elsewhere. But the anomalies keep accumulating. Every advance in observational capability reveals new discrepancies between predictions and reality. The universe consistently surprises us by behaving in ways our models do not anticipate. This pattern suggests something fundamental is missing from our understanding. What could that something be? The possibilities range from mundane to extraordinary. Perhaps our models of structure formation need refinement. Perhaps dark matter has properties beyond simple gravitational interaction that we have not yet discovered. Perhaps dark energy evolves with time in ways we have not properly modeled. Perhaps general relativity requires corrections on cosmic scales. These would be significant discoveries requiring new physics, but they would not overturn our basic cosmological framework. Or perhaps the issue is deeper. Perhaps the cosmological principle is wrong and the universe is not truly isotropic and homogeneous on the largest scales. Perhaps the observable universe is not representative of the whole cosmos. Perhaps we occupy an unusual region or an unusual epoch. Perhaps the constants of nature vary more than we thought possible. These possibilities would require more fundamental revisions to our theories. Or perhaps the truth is stranger still. Perhaps the anomalies are evidence of influences from beyond our universe. Perhaps other realities exist and interact with ours in ways we have only begun to suspect. The cold spot might mark where a bubble universe collided with ours billions of years ago. The dark flow might result from gravitational pull from mass concentrations beyond our cosmic horizon or in parallel universes. The Hubble tension might reflect interactions that affect expansion differently at different times or in different regions. The impossible structures might be patterns imposed during bubble collisions rather than structures formed through gravitational collapse. The galaxy alignments might reflect asymmetries created when our universe touched others. This explanation seems outlandish. It invokes entities we cannot observe directly and processes we do not understand, but it has the virtue of potentially explaining multiple anomalies simultaneously. If our universe is not isolated, if it has interacted with other universes during its history, and perhaps continues to interact now, many puzzling observations could find natural explanations. The multiverse hypothesis, once pure speculation, has become increasingly plausible as inflation theory has been tested and confirmed. If eternal inflation is real, bubble universes are inevitable. If bubble universes exist, occasional collisions are expected. The question is not whether the multiverse exists, but whether we can detect evidence of it. That evidence might already be staring us in the face. The cosmic microwave background, the largest structures, the galaxy motions, the expansion rate, all show features that strain or violate the predictions of standard cosmology. These are not subtle effects visible only in the most careful analysis. These are robust observations confirmed by multiple independent measurements. The universe is telling us something through these anomalies. Perhaps it is telling us that our models are incomplete in conventional ways, or perhaps it is telling us something more profound, that our reality is part of a larger structure, that we have neighbours beyond the cosmic horizon, that the boundaries we thought absolute are actually permeable, or at least have been permeable, in the past. The next decade will bring clarity. New telescopes and surveys will test these ideas with unprecedented precision. The Vera Rubin Observatory, Euclid, Roman, DC, SKR, CMBS4, LISA, and other experiments will map the universe in exquisite detail. Anomalies will either disappear as artifacts of insufficient data or will strengthen as robust features demanding explanation. If they strengthen, cosmology will face a revolution. The standard model will require modification or replacement. New physics will be needed, and that new physics might include the multiverse. If confirmation comes, if we conclusively detect evidence of other universes through collision signatures or other observable effects, it will be among the most important discoveries in human history. We will know our universe is not alone. We will know reality is incomprehensibly vast, extending far beyond anything we can directly observe. We will know that the strange behaviours we have catalogued, the galaxies moving wrong, the expansion accelerating mysteriously, the structures that should not exist were all clues to this larger truth. We have found billions of galaxies scattered across cosmic history. We have measured them, mapped them, studied their properties in every wavelength of light. But something is off. Something about how they move, how they cluster, how they evolve does not match our theories. For years, cosmologists have tried to explain away these discrepancies. But the anomalies persist and multiply. The universe keeps surprising us. The simplest explanation might be that we have been thinking too small. We have been trying to understand our universe as an isolated system when it might actually be part of a far larger reality. The billions of galaxies we have found, as numerous and impressive as they are, might be just one bubble in an infinite foam. And the strange behaviours we observe might be the echoes of cosmic contact, the marks left when our reality touched others. The universe has been trying to tell us this all along. We are finally learning to listen.